Unit Operation Classroom 8 2023 question 31. The position xt of a particle at constant omega is described by the equation this one. Okay. Uh, this is a very standard equation for simple harmonic motion. We'll look into that, where simple in the acceleration is proportional to here to the here negative of the distance or the displacement. So we have to find out a solution. It says the initial conditions are given at t is equal to 0. It's the value is a equal to 1, and the value of the slope at t is equal to 0 is 0. So we have to first find out the solution, and then we have to find out the position of the particle at this one. And so first we'll see the solution, and then you can, if you want, you can stop their video right there. And if you want to know a little bit more about the fundamentals of this equation, so you can continue on that video. So first, we'll look into the solution. So the solution is for this kind of linear second order differential equation is given by this, where a and b are arbitrary constants which have to be evaluated from, of course, the initial and the boundary conditions. So if this is the solution, we'll see that in little details later on. So the derivatives, of course, is this would be negative, and this would be positive of the cosine t, and we find out the derivative at t is equal to 0. This, of course, is equal to 0, and this, of course, equal to 1. So that makes 0 is equal to b omega. This is given as 0 here, b omega, and therefore, since that is equal to 0, since omega is not equal to 0, b has to be equal to 0. So it simplifies into a cos omega t. Now we apply this initial condition here, that x at t equal to 0 is a at cosine 0, which is equal to 1. So therefore a is equal to 1. So this is equal to 0, and this is equal to 1. So the solution is x is equal to cosine omega t. So that's kind of a sinusoidal function, as you can see here. This is x and this is t here. And as you can see, that the initial value is equal to 1, and the slope at t is equal to 0. This, of course, is t is equal to 0, is equal to 0. And we have to find out. So once we got the solution, we have to find out the displacement at t is equal to 3 pi over omega. We do that, and becomes cos over cosine of 3 pi omega. So that's 2 pi, 3 pi. So it would be negative. So that's negative 1. So the answer is, of course, equal to negative 1. So that's the answer. So answer is, so this is my answer. And if you want, you can stop the video here if you want to. If you like to know a little bit about this problem and its chemical engineering applications, you can continue. This is to find out the solution of this one. We'll discuss a little bit. So the standard second order linear ODE, ordinary differential equation, is given by this one, where a and b are constant coefficients. And so first we'll see what are the solutions under different conditions for this one. And then we'll just look into the special condition when a is equal to 0. If this a becomes equal to 0, then we get this equation here, which is the one given in our problem. So this is a special condition of this one here, where a is equal to 0. So we will try to see the solutions for both of these two systems under different conditions. So the characteristic equation is, of course, given by this one, and this, of course, is my discriminant, and let's call that as a delta. So delta is equal to, given by this one, where lambda and lambda 2 are the roots. Now, again, that's the solution we are looking into. That's my discriminant, okay? And lambda 1 and lambda 2 are the roots, okay? First one is, let's say, if this discriminant is greater than 0. If the discriminant is greater than 0, so we have two distinct roots. Yeah, these two are different, and these are real. the solution is given by this one. This is typically called an overdamped system, of course, and it will be stable if both lambda 1 and lambda 2 are negative, right? If any one of them, if both of them are of positive, of course, this is going to diverge. It's going to be unstable. Even if one of them is positive and the other is negative, then, of course, depending upon the relative values of C1 and C2, the nature of the system will vary, and that probably lead to instability also. So this is a very standard problem of CSTR with strong heat removal where there is no oscillation. So let's see, for a solution of this one, when the discriminant is greater than 0 as a positive, how this graph looks like. So if that's less yt and that's t, and if for the system, this is my solution, and it looks something like this. Okay, it goes, all right, goes towards equilibrium. Okay, if we assume this to be a deviation variable. Okay, now let's look at the second situation, B, where this is real and equal. So lambda 1 and lambda 2. So this is equal to, so this is equal to 0. So this lambda equal to 0. And so therefore we'll have lambda 1 equal to lambda 2. Of course, it's going to be equal to lambda. So that's that, and the solution is like this. Okay, again, it is going to be stable if this is going to be negative, right? As we can see that, and of course, if it is positive, then it is not going to be stable. This will lead to instability. This is called critically damped systems, and there is also optimal startup of or the shutdown of the reactors. We encounter situations like that if we do the modeling. So how does the curve look like for this key? This one, this one. Okay, so the for the curve B is something like this. So it goes this right line here. So this goes like this. So this is B. This is B. Okay. So this is my B, which is this one right here. So actually, this is showing here. That's not true. This is basically this one, right? Okay. Um, so this leads to fastest possible return to equilibrium without oscillation. So these are the two situations, of course, and here for this case, of course, both the roots are negative. Okay, so that's how it just comes. So we have both the discriminant greater than 0, discriminant equal to 0. The next situation is where the discriminant is negative. So again, we get complex imaginary roots, and this is the typical solution, and this is called underdamped systems. This comes when there's a PID controlled reactors, or we have the damped oscillation systems, then we get this kind of a solution. So let's look slightly in more detail. Um, so here we have the discriminant is less than 0. So if that is so, then we know that's the discriminant here. So we can write this one as this. Of course, this is my discriminant. So instead of this one, I'm writing that's equal to delta. Okay, that's okay. So if this is negative, then if this is negative, then we can write this one as I square, 4b minus s square. So if that's equal to, we know is -1. So we take the I out. So that's basically this one. Okay. So lambda becomes equal to this. Let's call this alpha plus minus I beta. So alpha is going to be equal to negative of a over 2, and beta is equal to this one. So this alpha, this real part here is responsible for damping of the growth rate. So that's what it dictates, alpha dictates. And beta, the imaginary parts, when there's an oscillation frequency, that's what it dictates. We'll look into the curves to have a better understanding and how that becomes important for our chemical engineering systems. So again, this is for the discriminant. So this is my main equation, and when the discriminant is negative, so that is my solution. And the roots are equal to alpha plus minus I beta. Alpha is equal to the damping growth rate, beta is equal to oscillation, A is of course responsible for the dissipation, and B is the restoring force, which just tries to restore it to equilibrium. Okay, if we had we more time, we could have taken one practical example and explained to you what are these dissipations and restoring force. Anyway, if alpha is less than 0, negative, which is the stable, desired one, This is the one. This has to be negative. That's what we design in our control system. This is called damped oscillation. And this becomes relevant when there is a well-tuned PID stable reactor applications. If alpha is equal to zero, if this becomes equal to zero, that of course equal to zero. So this is called marginal stability. We have a sustained oscillation. So we get the sinusoidal curve here. And this is typical of resonance or the cyclic columns. When alpha is greater than zero, so of course that will be unstable, and there's a growing oscillation, and there's a this possible runaway or flooding or the surge in the vessels, etc. So this is not desirable. This is also we tried not to. So this is the most desirable one under this situation when it is less than zero. Okay, let's try to see. So this is called underdamped systems. Okay, let's try to see how this curve looks like. So for C, when this alpha is less than zero, so that's less than zero, of course, going to be stable, desired one. Again, we like to say goal in the process industry that is to make this one negative and this value as high as possible. That lead to stability of the system, no overshoot and the oscillation or thermal runaway if we do that when alpha is less than zero. Okay, so first one, if alpha is less than zero, stable system, how does that look? So this is my curve C here. So this is my curve C. And as you can see here, this is my curve C. And let me try to find it out. This is basically this one right here. So that's my curve C. See how it leads to less of oscillation and leads to bring back to the equilibrium. That's my curve C when alpha is less than zero. And of course, delta is the discriminant is less than zero and alpha is less than zero. That's how the curve looks like. Okay. When alpha is equal to zero, for this equation, when alpha is equal to zero, this is called marginal stability. So we need to, so when alpha is equal to zero, that become to one, and that's a sinusoidal curve and the continuous oscillation, sustained oscillation. Okay. So that's what this one looks like. Take this one, this dotted line here. That's how it looks like. Okay. So that's my sustained oscillation. So that is my curve D when, of course, discount is negative and alpha is equal to zero. And when it's an unstable system, that means alpha is greater than zero, there's a growing oscillation. How does that look like? That looks like something like this. So the oscillation keeps on growing. So it leads to instability. So as you can see, if this is greater than zero, that will just keep on increasing and that will lead to instability of the system. Okay. So what are the types of solutions? So let's look into this one. So as we say that this is the standard second order linear ODE, and the special case of when A is equal to zero, that means this term vanishes. So this is my solution here. And we can write this one as omega square y. That is the given problem. Problem is given. So that's what this is. When omega square is greater than zero, then solution is this oscillatory simple harmonic motion. When omega square is equal to zero, when omega square is equal to zero, we get this one right here. This is called neutral or the drift, depending upon the C1, the C2 value. It can be just something like drift like this way, or just go this way, or can go this way, depending upon the comparative values of C1 and C2. When omega square is less than zero, it might be just a value. You might think of like how a positive number can be less than zero. Square can be a less than zero. It's the value of the omega square that is important. Okay, overall value. So if that is negative, then we get this equation right here. Okay, and we have seen how that leads to unstable exponential rise in the deviation, or the leads to instability. So let's look at this one. So this is omega square. So that's a simple harmonic motion here when omega square is greater than zero. When there's a when there's a in neutral drift, okay, this could be something like this, or this could be something like this. And when there's an unstable system, it just keeps on increasing like this. Okay, so these are the three systems. So anyway, so these are just simple equations. So this is very important for our system, and you might have seen that this is the equation which you have used in the problem. So this is the equation. So going back here to the original problem. So this is, see, this is the equation what we have used. Okay. And we have used this one, and of course the solution is -1. So the answer is -1. That is my answer. Okay.